right, here we are. Confidence intervals for proportions. Let's do it. Let's get into it. The last video we were just talking about confidence intervals in general and how they behave and kind of what they are, what they do. But now let's actually get into it for this specific situation, right, with proportions. Before, though, we get into the actual example, we've got three requirements that we have to make sure are there to do this, okay? The first two we've talked about before, kind of makes sense, right? Samples, whatever we're measuring, typically it's always given that they're proper and random, right? Properly random, adequately random. That's always given, right? You can pretty much always assume that in this class. But when you go out in the real world, this is always something you have to be looking into, checking into, right? You want to make sure there's no bias. The second one here is that there's only two outcomes, right? In this case, we're looking at proportions, right? This rule set here, more or less, is for proportions. This one here is always just like the golden rule in statistics. But we're more or less looking at specific to proportions. But in this case, there are only two outcomes, meaning that if we kind of go back to, that brown thrasher example, right? We were looking at the proportion of brown thrashers, and the proportion of everything else, we were not getting specific with the everything else, right? It either is a brown thrasher or it is not, right? We're not looking at brown thrashers and mountain chickadees and Stellar's jay and scrub jays and whatever, right? We are only looking at those two outcomes, whether it is or isn't a Stellar's jay or a brown thrasher or whatever the bird was. And then this one, very specific to proportions. N times P hat has to be greater than 15, greater than or equal to, or N times 1 minus P hat has to be greater than or equal to 15, or normally distributed. This is easier to test than this. But what the hell does this mean? Well, all that's saying is that there should be at least 15 observations for both things, right? In the case of the brown thrasher, we want to see that there are at least 15 brown thrashers and 15 other things that are not brown thrashers, right? For a total of 30 observations. Again, kind of arbitrary, this whole idea, but that's just kind of a rule of thumb in this scenario, in this situation. So total sample size 30, and both outcomes should have at least 15 occurrences. Okay, pretty easy to test, right? Pretty easy to test if you're given the proportion straight out and given a sample size. All you have to do is multiply them together, and they should be at least 15 for both of them, right? Sometimes you're given like the actual number for both, which is very easy, right? If any of these are violated, you have to stop, right? You should have already checked for it in the beginning, right? So if you're doing like a hypothesis test for proportions, or any kind of hypothesis test, typically you want to check these first, and then move on with all the work, right? I won't ever give you a situation where like you do the whole thing and then turns out that you missed this or whatever, and then everything you just did was totally pointless. I think that's pretty rude to do that. But in real life, do make sure that you're checking for these things. All right. Again, a little bit of review. The general idea here with the formula, right? We have our Z table more or less right here for our alpha and our confidence level and the respective Z critical value. We most likely will have this or have already calculated this, or it's given to us. We just kind of have to calculate that. Well, what is that formula? Well, the standard error for proportion, for sample proportion, if we're being very specific here, is this thing, and it's not that bad. In fact, it's kind of similar to what we've seen before, right? Where P hat is the sample. 1 minus P hat is everything that, is not covered by this. And then N is given, right? But that's just the sample size, right? Easy peasy. So all you got to do is plug and chug, and then multiply whatever the standard error was to whatever your Z-crit is, and then add and subtract it to your, in this case, sample proportion. And that's going to give you an estimate, or at least a range, of all the possible values that your population could be, which is pretty cool, I think. Okay, here we are. Let's do it. Let's do it. Okay, so in 1998, a national survey was sent out asking whether people believed there was an organization that supervises extraterrestrial life forms who live on Earth and hide their existence from ordinary humans. It also just so happens that Men in Black came out the year prior, 1997. This is true. This is real. This is a real thing. I think Reader's digested it. So it turns out that 55% of their sample, which contained 1,114 people, said that they do believe in that. They do believe in that. And we'll assume that they did a hypothesis test on this against 0% of people believing it, and we'll assume that that p-value ended up being less than 0.05. Okay, so this is all statistically, significant. And our job is to calculate a 95% confidence interval to determine the range of values that the whole population. So in this case, the national survey will assume that it's the U.S. It could be any country, it doesn't matter. But we'll assume it's the U.S. in this case. And we want to figure out how many people, right, or what range of values could the U.S. population be as far as this, who believes in Men in Black or not. Okay, so let me actually do this. Let me make a new page so we can have some fresh work. And what I'll do, take these because we need this. Put that here. Easy peasy. I'm also going to grab this so we can see it. Beautiful. Cool. Okay. And then I'm going to write out we're looking for a 95% confidence interval, right? That's the idea. And we see that the z-crit here is going to be 1.96. Easy peasy, right? Easy peasy. What do we want to find first? We know our sample proportion is 55%. We know our n is 1,114. Our z-crit's 1.96. Let's just find the standard error first, and that'll make plugging and chugging much easier. Okay. I'm gonna get rid of this. Zoom in just a little bit. Beaut. Okay, so our standard error from up here is going to be p hat. Okay, so let's see, 0.55. I'm doing this slightly out of order. And then 1 minus 0.55 divided by n, which is 1114. And then this is all underneath the square root operator. Okay, and let's see. So I've actually got this calculated ahead of time. But it turns out that this equals 0.15. 0.15. Okay, so again, I've said this before, I'll say it again. Be very careful with your order of operations here. Know that you're supposed to multiply these together first, or first do this, 1 minus that, and then multiply them together, and then divide, and then take the square root of all that, right? Calculators make this much easier, but do keep track of your parentheses and such, okay? Dope. That's it. That's it as far as finding everything that we need, right? So let me do this in this cool green. Heather green or hunter green? I think, isn't heather like a pattern? Send me an email. Okay, so our 95% confidence interval, okay, is going to look like this, where it's going to be p hat plus, and actually let me do it this way. We'll do minus first, okay, and then 1.96 times our standard error, right? Or even if we're being super general. Okay, that's the general form. Do it again. Down here, it looks like this. Dope, right? No problemo. Let me get rid of all this. So then what we're going to do is, let's calculate the lower bound first. So that's going to be 0.55 minus, and I'm going to be, let me just show you quickly with the parentheses. This whole side is being multiplied together first, right? So that's going to be 1.96. Okay, so that's the z. This is the p hat. And then our standard error, 0.015. Right, so we multiply these together first and then subtract. Okay, so let's see. It turns out, let me run this again. I've got the math open on another screen. This lower bound, oh, Lord almighty. Oh my God, what the hell? Sorry. Is 0.52. That's the lower bound. So highlight that. Cute. Very cute. Let's do it again for the upper. Same deal, except we're just adding this time, right? So same values. 0.96. 0.015. Standard error, z-score, right? Plus, and that turns out to be, what does that turn out to be? Ah, beautiful. 0.579, so 58. We'll say two decimal points is fine. Okay, now let's write this out. Did I run out of room already? Gosh, I'm writing like an ape today. Cool. No worries. So cool. All right. So our 95% confidence interval for this is 0.52 to 0.58. Okay. So what we're saying is, let me be kind of delicate here. We are 95% confident that the true population, and let's be specific in this situation, that the true population proportion for people in the U.S. who believe in Men in Black is between 50, and let me use this color, 52% and 58, 58%. We are 95% confident that the true population proportion for people in the U.S. who believe in Men in Black is between 52% and 58%. And that is it. Right? So we did this whole thing where we used a summary statistic, right? This sample proportion in this case. We used the z-score. We used the standard error. We used the z-distribution. We've been doing all this stuff for now a month, for like 4 weeks, right? To bring it all the way back to estimating what a whole population would be, right? We've got this range of values that we think it could be in, right? And so let's just kind of recall here too. Our p-hat, our sample proportion was 0.55 or 55%. Now it's not smack dab in the middle. Let's see, is it? Almost, yeah, it's almost smack dab in the middle. Sometimes it will be symmetric like that. Sometimes it won't be. And that's okay, right? It's all about how the data look, right? But check it out. Like we're pretty close. We're pretty close to this value, right? We've got a very high sample size, so that's great. And we're only just a little bit away on each end, right? We're pretty close to this. Now what I'm saying here, that this is not the actual population, right? This this value only represents what our sample was. And we had evidence to say that, all right, we found that this sample was this sample, the sample proportion. The known value was, I guess, 0% in this case. But then we're saying, all right, we got enough evidence to say that, based on this, it's probably closer to this. What is that range of values? It turns out that it's between 52 and 58%, right? We're 95% sure that if we were to go and repeat this experiment a bunch of different times, 95% of the time, our sample proportion will be between 52 and 58%, 95% of the time, which is pretty freaking cool. We finally have gone back all the way from the beginning, talking about what populations are, what they look like, how you sample, and we've finally gone back and brought it all and tied a real nice little bow at the top of this statistics present or whatever. Cute. Okay, so I think I might leave it. Yeah, okay. I'm gonna pause it there, and we'll pick up here in just a second for part 2. I'll see you there in a little bit.